So we've looked at how to do the derivatives of exponential functions that have base e and logarithmic functions that have base e. So now we're going to take a look at how you find the derivative of exponential and logarithmic functions when your base is some number other than e, including if we have to use the chain rule for composite functions, or if we have to combine them with other derivative rules. So let's take a look at logarithmic functions first. So if we want to take the derivative of a logarithmic function that has some base other than e, let's follow the same kind of procedure that we worked on when we were doing the derivative of the natural log function. And we're going to start with a derivative that we know and try to work our way to a derivative that we don't know. So we know that if our function is y equals ln x, and we're working with base e, or the natural logarithm, we know that the derivative is 1 over x from the last lesson. So if we have a function that is y equals log, and I'm just going to have our base be a here, where a is just some number, so base a of x, we can take this logarithmic expression and turn it into an expression that uses the natural logarithm using the change of base formula. Now, we'll use the change of base formula this time so we can figure out what the derivative rule is, but you don't have to use it every single time. Once you know the derivative rule for bases other than base e, you can just apply that rule. So the change of base formula allows us to go from a base that we have to any other base. So applying that formula, this would become, if we want to go to the natural logarithm, we would have ln x over ln a. Okay? The log to whatever base we're changing to of our argument, x, divided by logarithm to whatever base we're changing to of our old base. Now, when we look at this, the denominator here, ln a, remember that a is just a number here. So ln a is just a number. So our entire denominator here is a constant. So to make this a little easier to take the derivative of, let's just rewrite this to pull that constant out in front. So we've got 1 over ln a. Ln a is just a number. 1 over ln a is just another number, times our function here, which is ln x. So now let's take the derivative here. We've got a constant times a function, so we know that the derivative is just going to be the constant, 1 over ln a, times the derivative of the function. And we know that what the derivative of ln x is. It's 1 over x. So we can put these things together, sort of multiply these two fractions together to get 1 over ln a times x. And that's our derivative rule. Okay? If our function is log base a of x, then our derivative is 1 over ln of that base, whatever that base happens to be, times x. Okay? So it's like you've got the same derivative rule. It's 1 over whatever the argument of your ln function is, but you've just got this other factor of ln of your base working itself in there to sort of compensate for the fact that you're not working with base e anymore. Okay? Now, again, if we have the chain rule, if we're doing log to the base a of some composite function g of x, well, we know how to apply the chain rule here. It's going to be 1 over ln a, okay, to account for the fact that we're not using base e, over g at x instead of x, times derivative of that inner function, g primed at x. It's that stuff in the red box there that you actually need to know and be able to apply. So let's take a look at some examples here. So our first one, pretty straightforward. Y equals log to the base 2 of x. Okay. Straightforward application of the derivative rule. It's going to be, our argument there is just x, so it's just going to be 1 over x with this other factor of ln of whatever our base is. So our base is 2, so it's going to be 1 over ln 2 times x. Okay. Now, I guess I should make this a little bit more clear. Remember, we're only taking the ln of that 2, okay? That x, we're not taking the ln of the x. Okay? All right, something a bit more complicated. Y equals log to the base 5 of x cubed minus 2x squared plus 10. Okay. We got to use chain rule here, okay? We've got a composite function. Our outer function is log to the base 5. Our inner function is, let's write it out here, we'll call it g at x, is x cubed minus 2x squared plus 10. We can do the derivative of that pretty easy. That's going to be 3x squared minus 4x. So our derivative of our whole thing here, y prime, we need to have 1 over our base is 5, so we're going to have ln 5 times that inner function g at x. So ln 5 times x cubed minus 2x squared plus 10. Okay, and then our chain rule, again, that looks a little bit weird. I should probably put this in brackets. That whole thing has got to stay together like that. And then I'm going to multiply this by the derivative of that inner function, which we've already calculated, our 3x squared minus 4x. So times 3x squared minus 4x. And I'll put that in brackets too. So if you wanted to clean this up a bit, of course, you could write this as a single fraction, 3x squared minus 4x all over ln 5 times x cubed minus 2x squared plus 10. Okay. All right, let's do a hard one here. Y equals x cubed times log to the base 2 of the square root of x squared plus 4. What rules are we going to need to use here? It's like all of them, right? We got to use product rule. We got to use chain rule. We got to use our logarithmic derivative, and we've got a power function here. So this is almost everything that we've seen. How would you start this? I would probably, well, what would you do first here? What do you do when you see the square root? Ryan? Yeah, so let's change that to a 1/2, an exponent of 1/2. So our function is going to be y equals x cubed times log to the base 2 of x squared plus 4 all to the 1/2. Okay. We can simplify it a little bit more, again, using one of our laws of logarithms. In the last lesson, we used the division law, the quotient law, or the quotient rule. Here we can use the power rule. If we've taken the log of something to some exponent, we can bring that exponent out in front of the logarithm. So this becomes x cubed times 1/2 log to the base 2 of x squared plus 4. That's going to make our derivative a little bit easier to do here, okay? Because that means we don't have to, that function that is inside our logarithm is no longer a composite function. So from here, product rule, okay? U and V, so our derivative is going to be U primed 3x squared times our V function here, 1/2 log to the base 2 of x squared plus 4 plus our U function, x cubed, times the derivative of V. So when we do the derivative of V, we're going to have to use the logarithm rule, and we're going to have to use the chain rule here. So we've got a constant of 1/2 out in front, so we're going to have a 1/2. Derivative of the log function is going to be 1/ln 2, because we're working with base 2, times x squared plus 4. And then we want to multiply by the derivative of that inner function. Inner function is 2x plus 4, x squared plus 4, so its derivative is going to be 2x. And then maybe we can simplify this a little bit. We've got a 2 there, which is going to cancel this 1/2 here. So we can sort of write this as 3/2 x squared log to the base 2 x squared plus 4 plus, see, x cubed times an x is going to give us x to the power 4 over ln 2 x squared plus 4. And that's probably as far as we would go, unless we had a specific reason that we wanted to simplify it further. We could factor, if we wanted to, we could factor out an x squared. But most of the time, I think we'll just leave it like that. Okay. That's logarithms to some base other than base e. So what if we want to find the derivative of an exponential function that has a base other than base e? Well, think back to where we started in this unit. This was actually the question we had at the very beginning. If we have some function, y equals a to the x, a general exponential function, and we wanted to find the derivative, in our very first lesson, we went through this long process applying first principles, and we said that the derivative was equal to a to the x times the limit as h goes to 0 of a to the h minus 1 all over h. And we didn't know how to evaluate this limit here, okay? Which led us to figuring out that, hey, that whole limit was equal to 1 if we were using base e, and isn't base e really, really nice, and why don't we use it all the time? Well, we can't use it all the time. Sometimes we're going to have a number in there that is something other than base, than e. So how can we figure out how we're going to do this derivative here? Once again, we're going to start with the derivative rules that we've already learned and see if we can use them. Now, what I'm going to do here is I'm going to rewrite this function by using a little trick here. I've used this a couple of times before, but if I've got something like e to the exponent ln 2, okay, remember that exponent to some base and logarithm of the same base are like inverse operations. So if I have e to the ln 2, it's like the e and the ln cancel each other out. And my answer is just 2 here. So I'm going to use that trick, and I'm going to rewrite this function here, y equals a to the x, as y equals e to the ln of a to the x. Okay, so I've gone from y equals a to the x, I've stuck in an e, and I've also stuck in a ln, which basically cancel each other out. Okay? Now, I've made my function more complicated. So why would I do this? Well, if I just look up at the exponent here, ln a to the x, I can apply my laws of logarithms. I'm taking the ln of something that is a to some exponent, so I can bring the exponent out in front and write this as e to the x ln a. Or even better, I can write it as e to the ln a times x. Because remember, a is just some number, so ln a is just a constant. Okay? Ln a. So now, let's take the derivative here. Okay? I know how to take the derivative of a function, an exponential function that has base e. Okay? It's going to be the original function, so e to the ln a times x, times the derivative of what is up in that exponent there. So what is the derivative of ln a times x? Well, it's a constant times x, so it's just going to be ln a. Now I can sort of undo the stuff that I did before, okay, to my exponent here. So I can take my e to the ln a times x, and I can rewrite it as e to the x times ln a times ln a, okay, e to the ln a to the power of x, okay, applying the power law in the opposite direction, again, times ln a. And then, back where I started from, the e and the ln cancel each other out. So my final expression for my derivative is a to the x times ln a. So what does all of this mean? It means that if you start with the function y equals a to the x, your derivative is your original function, a to the x, times the ln of the base. So again, just like with the logarithmic functions, you have this extra factor of ln a coming in to account for the fact that you're not using base e, you're using something other than that. And if we go back up to the expression that we had from first principles, our work with first principles told us that our derivative was a to the x times something, this limit. What is this limit? Well, this limit actually always evaluates to ln of whatever your base is. Okay? So this is why it works out so nicely when you're using base e, because the ln of base e is just 1, so that limit evaluates to 1. Okay? Nonetheless, what do you need to know? Well, you need to know this derivative rule, and you need to be able to combine it with the chain rule. So if you got something like y equals a to the g of x, your derivative is going to be, again, your original function, a to the g at x, times ln a, to account for the fact that you're working with a base other than base e, times g primed at x, because you're doing the chain rule. So that stuff in red is the stuff that you need to be able to apply. Okay. Right? So let's take a look at a couple of examples here. First one. Y equals 2 to the power of x. Okay? This is going to be a direct application of that rule that we just wrote down. Okay, so if y is equal to 2 to the power of x, what is our derivative going to be? Exponential function. So the first part of the derivative is always going to be whatever that original function is. Okay, so our original function is 2 to the x, so our derivative is going to be 2 to the x times what? Well, times ln 2, because we don't have base e, so we have to multiply by this factor of the ln of the base. Okay. Next up here. F at x equals 3 to the x squared plus 2. So we've got an exponential function, base is 3, and it's a composite function. Okay? Our inner function is that x squared plus 2. So what's our derivative going to be? Well, exponential function, first part of the derivative is always going to be the original function, 3 to the x squared plus 2. We're going to multiply it by ln 3, because we're not working with base e. And then we're going to multiply by the derivative of that inner function. Our inner function is x squared plus 2, so we multiply by 2x. And there's our derivative. Okay, so we'll finish here with one that is a little bit trickier here. F at x equals the cube root of 3 to the x divided by x squared. So I think this one we want to rewrite it before we try to take the derivative. How would you rewrite this thing? I think there's two things we want to do here, Van. Root to 1 over 2. All right. So we could write it as 3 to the x to the 1 over 2, all divided by x squared. What else can we do? Okay, right? Yeah. So we'll do x to the negative 2. And the other thing we can do is we've got a base 3 to some exponent to another exponent. So we're doing the power of a power, so we can multiply those two exponents together. So this is going to be 3 to the x over 2 times x to the negative 2. So now we can start taking our derivative here, f primed at x. Right? We're going to have to use product rule, because we have two functions of x multiplied together, u and v. All right, so what's the derivative of our u function? Well, let's see. It's an exponent to some base other than base e, so we're going to have 3 to the x over 2 times, again, ln of our base, ln 3, times the derivative of that inner function. So what is the derivative of x over 2? We can think of that as 1/2 times x. So the derivative there is going to be 1/2. And this all gets multiplied by x to the negative 2. To this, we should add, we need our original function u, so 3 to the x over 2 times the derivative of v. So x to the negative 2, we bring down the negative 2, and make it x to the negative 3. And there's our derivative. Now, exponential derivatives, we can almost always factor these, because we're going to have a 3 to the x over 2, which is common to both of these terms. So we could factor that out. What else can we factor out? Well, we've got a power of x that is common to both terms, so we can factor out the lowest power of x, x to the negative 3. That's going to leave us with 1/2 ln 3 x from that first term. And then from our second term, we've taken care of the 3 to the x minus 3 to the x over 2. We factored out the x to the negative 3. So we're just left with the negative 2. Okay. And there's our derivative. Okay. So if we wanted to simplify to get rid of that negative exponent, we could change all of this back to 3dx over 2, 1/2 ln 3 x minus 2, all divided by x cubed. And that would be our final answer.